We're going to solve a large order homogeneous linear differential equation using GeoGebra. So this looks a little bit nasty, but actually the problem is very straightforward. We do the same process that we did before. We're just going to use GeoGebra to help us factor the characteristic equation that we're going to get, and then we'll go through and write down the solution. So notice that we have this 10th order linear differential equation, which means that we're looking for 10 linearly independent solutions to be able to write the general solution. So the first thing we would need to do is figure out what the characteristic equation is. And of course, that's a pretty straightforward process because we end up just replacing all the derivatives of y with powers of a variable. So our characteristic equation would just be simply taking all of these derivatives out and replacing them with the appropriate power of x or m or what have you, whatever variable you want to use to solve this equation. So our characteristic equation, I've already got that typed into GeoGebra for us. Well, I got our characteristic, I don't have the equal to sign, but you can see it in here that you've got x to the 10th, 14x to the 9th, 114x to the 8th, and so on down the line. Just replacing all of those y, the derivatives of y, just go back over here again, replacing all of these derivatives of y with the appropriate power of a variable. Again, use whatever variable you like because we're just trying to solve the characteristic equation. We used m quite a bit in class. Here I've already got it typed in as x on GeoGebra. Notice that I'm factoring it because what I really want to check is to see if there's any multiplicities. So notice that when we factor this, we've got an x plus 2 to the 4th. So we have a repeated root here, and it's repeated 4 times. Over here we got an irreducible quadratic term, and each of those roots are going to be repeated 3 times. To figure out what those roots of that quadratic are, I'm going to use the csolve command. And I'll do the x squared plus 10x, or excuse me, plus 2x plus 10 equals 0. And we get that the solutions are -1 plus 3i and -1 minus 3i. So we've got 3 actual distinct roots, and then we've got some multiplicities. We've got a root of -2, that's coming from the x plus 2 factor. And then we've got these roots of -1 plus 3i, -1 minus 3i, and remember we handle those using the products of an exponential and a trig function. So, just to write this down again, our solutions to the characteristic equation, we've got, I'll use m because we typically use that in class, we had -2, and we've got -1 plus or minus 3i. Let me just double check and make sure I did -1 plus or minus 3i. This one had a multiplicity of 4, and these had multiplicity 3. So this root, the -2, this root right here, is going to contribute 4 terms in our general solution, and each of these complex roots will each contribute 3 terms in our general solution. That's where we're going to get our total of 10. So the way we handle these again, just to write these down, our y will be c1 e to the -2x, that's for the -2, and then we've got to multiply that by a power of x for each extra multiplicity. So we get that c2x e to the -2x, a c3x squared e to the -2x, and a c4 x cubed e to the -2x. That's how we handle that -2 being repeated 4 times. So now we need to do the complex roots. And remember we handle that as e to the, this number here times x, so in this case it'll be an e to the -x, and this goes inside as the argument of the trig function, the cosine of the sine. So we'll get a plus c5 e to the -x cosine 3x and a c6 e to the -x sine 3x. And then since we've got multiplicity 3, I need to multiply each of those by an x and by an x squared to get our other linearly independent solutions. So we'll finish this off by doing c7 x e to the -x cosine 3x, c8 x e to the negative x sine 3x, C9 x squared e to the negative x cosine 3x, and C10 x squared e to the negative x sine 3x. And that would be our solution.